Continuing on, we're now talking about magnetic force on a current carrying conductor. And again, we have to talk about how to determine the direction of force or the direction of field or whatever we're talking about. And problem number 31 is very much like what we just did previously, but now we're talking about a current, which is something that's captured within a wire. However, the concept is the same. Your fingers go in the direction of the field and your thumb goes in the direction of the current, and then the force will be your palm. So for the first one, you're pointing into the page, coming out of the page, excuse me. Your thumb is going down, and therefore the palm is directed to the left. And so A is left. B, your fingers are to the right, your thumb is up, so your palm is into the page. The palm is into the page. And so the force is into the page. C, the fingers are going into the page. The direction of the current is to the right, and so your palm is up. And so the answer to C is up. D, they're not perpendicular, and therefore there's no force. E, now the current or the field is going up, and your thumb is going into the page. Okay, and so that means you're to the right. And then the answer to the last one is down. And again, if you don't understand these, we can go over these again in class. Number 34. What is the force per meter on a lightning bolt that's at the equator carrying 20,000 amps perpendicular to the Earth's 3 times 10 to the minus 5 Tesla field? Okay, so for A, the formula for this is that the force, and this is very similar to the previous formula, but it's going to equal IL beta. Now, sine theta, and again, theta is anything outside of being perpendicular. I being the current, L being the length, beta being the field. Now, they ask the force per length, and so you end up with IL. And so in this case, it's going to be 20,000 times 3 times 10 to the minus 5, or 6/10 of a Newton per meter. B, what is the direction? Okay, if the force, what is the direction of the force? And it says the current is straight up, so your thumb is straight up, and your field is due north parallel to the ground, so your fingers are due north. Your palm is facing to the left, which in this orientation would be west. Number 36. Number 36 states, what is the force exerted on water in an MHD drive utilizing a 25 centimeter diameter tube if a 100 amp current is passed along that tube, across that tube, perpendicular to a 2 Tesla field? Basically, again, we use this formula. It's perpendicular, so you don't have to consider that. And in this case, L is going to be the diameter of the pipe. Okay, so you've got 100 amps, and the diameter pipe is 25 centimeters or 0.25 meters, and it's a 2 Tesla field. So that's going to be 200 times a quarter, or 50 newtons. 50 newtons. Next, Number 42. With number 42, we're now talking about torque. Now what that means is if you have a loop like this, we'll make it a square loop. When you pass this through, you have a current passing through an electric field, it causes this loop to rotate. And that's what the torque is the force of rotation for this loop. We'll talk about this more when we talk about motors and generators. But the torque, now most of these don't have a single wire. They have multiple wires. So the torque is going to be equal to the number of turns of wire times the current that's going through this times the area of this loop times the field it passes through. And as it turns, it goes through various levels of being perpendicular. So the maximum is going to be when this is equal to 1. So it says in number 42, it says, what is the maximum torque of a 150 turn square loop of wire, 18 centimeters on a side, that carries a 50 amp current in a 1.6 Tesla field? So it's telling you that this is 18 centimeters. So what you have is the torque, maximum torque, is going to equal to 150 turns times a 50 amp current times 0.18, and the area is going to be that squared times 2 Teslas, which is what, or excuse me, 1.6 Tesla. 1.6 Tesla field. So if you put that in there and you do the calculation here, you get 389 Newton meters of torque. Torque is Newton, is the label for torque is Newton meters. So 389. Number 43. Number 43 states, find the current through a loop needed to create a maximum torque of 9. The loop has 50 square turns, 15 centimeters on a side, and a uniform 8. Okay, so you basically, this is the same kind of problem, except now we're solving this for I. And if we solve this equation for I is going to equal the torque divided by the number of turns times the area times the field. And this again, it's talking about maximum, so we don't have to worry about the theta here. The torque is 9. The loops is 50. The area is 0.15 squared. And the field is 0.8 Tesla. And it turns out that that works out to exactly 10 amps of current. Number 47. Number 47 says, a proton has a magnetic field due to a spin on its axis. The field is similar to that created by a circular current loop that's 0.65 times 10 to the minus 15 meters in radius. Okay, so radius is 0.65 times 10 to the minus 15. So the area is going to be pi r squared, because we're going to need the area. Find the maximum torque of the proton in a 2.5 Tesla field. Okay, so for this problem, the torque, again, maximum, so it's going to be nav, okay, times I. So that's going to be, the I here is given as 1.05 times 10 to the 4. So it's, N is, you assume that N is 1, because it's just one electron. So it's 1.5, 1 times 1.5 0.05 times 10 to the fourth times, and it's a 2.5 Tesla field, and the area is pi times 6.5 times 10 to the minus 16 squared. And if you do all of this math, you get the torque here is going to be 3.48 times 10 to the minus 26 Newton. Now with number 52, we're moving into the force with two parallel conductors. Okay, if you have two conductors that are conducting electricity, because they both generate an electrical field, there's a force between them, and if they're in the same direction, the force is an attractive force, and if they're in opposite directions, it's a repulsive force. And so the force per unit of length is equal to a constant, mu0, times the current in one times the current in the second one, divided by 2 pi over the distance between the two wires. And it turns out that mu0 is equal to 4 pi times 10 to the minus 7. Okay, so the first problem is problem number 52. A 2.5 meter segment of wire supplying current to a motor of a submerged submarine carries a current of 1,000 amps and feels a 4 Newton force from the parallel wires 5 centimeters away. What is the direction and magnitude of the current in the other wire? Okay, so if you know one of these and you need to know the other, okay, and you know the distance here. So the force, since they give you a length of it, the force is going to be equal to mu0 I1 I2 L over 2 pi times the distance. And so if we rearrange this to solve for I2, you end up with 2 pi r, that's multiplying over here, times the force, divided by, so you move this over here, and then you divide by everything here except for I0, so it's going to be mu0 I1 L. So it's going to be 2 pi times the distance between them, which is 0.5, excuse me, and this is, the force was 4 newtons, and on the bottom, it was 1,000 for I1, the length was 2.5 meters, and mu0 is 4 pi times 10 to the minus 7. So I2 ends up being 400 when you do the math. So I2 ends up being 400. Okay, we're going to do one more, then we'll switch and finish off the last one on the next tape. 54 is very much the same as 52. 54 states an AC appliance cord has a hot neutral wire separated by 3 millimeters and carries a 5 amp current. When you have hot and neutral, that means that the one direction is 5 amps and the other direction is 5 amps. What is the average force per meter between the wires? Okay, the average force per meter, which is F over L, is equal to mu I1 I2 over 2 pi r. Okay, so you're going to get 4 times 10 to 4 pi times 10 to the minus 7 times 5 amps squared, because it has to be the same in both directions, over 2 pi times the distance between them, which is 3 millimeters, and it's going to be 1.67 times 10 to the minus 3 newtons per meter of length. Now, it says what's the maximum. Remember, with AC current, that VRMS, or IRMS, I guess I should say, which is what we're given here, is equal to I max over the square root of 2. And since we're doing it twice here, what that means is that the answer here is going to take this and just multiply it by 2, because you'll be multiplying in each case by a factor of the square root of 2, and the square root of 2 times the square root of 2 is equal to 2. So it's going to be 3.33 times 10 to the minus 3 newtons per meter. C, they're headed in opposite directions, so it's a repulsive force. And D, because the force is small, it doesn't have a big effect. And you don't have to have anything special to keep the two wires from splitting it apart.